Hey, Ben Harris is with us this morning. It's Thursday, November 19th. Yeah, well, I guess that's pretty good. I'm always amazed when this computer actually works. Yeah, let's see
Professor,
what we got on board here. We got, oh, look here, Braxton, Ben Seaman, Ashley, Ben Harris, Alex. We got a class. And, oh, it's time. It's time to get going on our class. What do we got?
Professor,
Yeah, go ahead.
I was just asking for the test, does it matter if we just print out the test and write it on there, or do we need to write it on engineering paper?
Oh, you can do it either way. I really like it on the test, but if you don't have enough room, you can send me another page. It's okay. Just so the answers are right.
Okay, sounds good.
You were supposed to laugh, but that's all right. Now, who was that I was just talking to?
This is Ben Harris.
Ben Harris. Nice going, Ben. Uh, what I need to know is, did you get that exam? Is it available and you're able to pull it up, Ben?
Yeah, I've already completed it.
Wonderful, wonderful. Well, good luck on sending it in. I think that link will work okay. Good deal. I'm sure you'll do just fine. Uh, so let's see where we are. The test is available. I think it was available Tuesday, wasn't it? And so let's see, the night, November 19th. The test was available to say, yeah, it was available Tuesday and it's due Friday at midnight. So a lot of you are done already. Good going for you guys. Today we're starting on some new material here, pressure vessels, chapter 19. There's some homework as always. Let me put that on the board. It looks like not chapter 9, chapter 8. We're going to start on chapter 8. And the homework is homework number 28. And it's problem chapter 8, problem 2, and also problem 10 on chapter 8. Well, we're going to talk about chapter 8. The topic today is pressure vessels. Okay. The chapter, I think, is on general loading. Let me look and see. Chapter 8. Did anybody have another comment or question for me? Yeah, the topic is really is chapter 8, which is, they call it combined loadings. Combined loadings. I call it general loading. Same idea. Let's have a quick review of the different kind of loads that we have and some of the equations we know. You're all familiar with this one. Take the normal force and divide it by the area, and you've got your normal stress. And then there's one that looks like this. And that's called the torsion formula. And that's when a body is being twisted, you've got some shear stress because you've got some internal torque going on. This rho here is the distance from your centroid of your piece that's being twisted. And this J here is called the, it's got a name. I could ask any one of you guys and you could remember it, but I can't. Just a minute. It's called the polar moment of inertia. It's the you might have forgotten that. And then there's this one here. And that's our flexure formula. You get that when you have bending loads. See, these are torsion loads. These are normal force loads, usually on an axial member. These are torsion loads. These are bending loads, and you get normal stress, and you also, with bending loads, you get more for your money. You get two different kinds of stresses. We're having a little 5-minute review. Now, in order to find this normal force, what you have to do is you have to make a normal force loading diagram. That equation there, you need a normal force. I hope I'm boring you. I hope you know this stuff so well that, why is he doing this? I know all this stuff. You need a normal force loading diagram. And we've done these. You've made these. And then to use this equation here, see, that's the normal force. This here is the torque. And to use that equation there, you need a torque. You need a torque loading diagram. And we've done that. We've made those. You know what? We started off this little adventure of ours August 17th. Can you believe that? August 17th, September 17th, October 17th, November 17th, and this is the 19th. We've been going at this for a long time. And this here, for that one, that's called the flexure formula. You knew that. I could ask any one of you. I could shake you up from a sound sleep and ask you what that is. And you could say, Mr. Griffin, that's a flexure formula. You know this stuff. And see, to use that one, you've got to make a bending moment. Loading diagram. And this equation here has a name too, and we've recently been doing it. It's called the shear formula. That's the name of it. It's the shear formula. And it gives you shear stress if you have bending. You know what? If you have torsion, you can get shear stress. And if you have bending, you can get shear stress. Isn't that interesting? And long ago, I think I showed you, even when you just have a normal force, there is some shear stress internally, even in a member that is only under tension, for example, or compression. I gave you those equations. So we've come a long way. And what we've been doing all this time is we've been pretending you just have one kind of loading. Wait a minute, isn't there 4 different kinds of loading? I thought there was 4. Maybe not. Oh, well, I guess that's it. I thought there was 4 kinds of diagrams: a normal force diagram, torque loading, torque loading diagram, bending moment loading diagram. Oh, yeah. There's a shear loading diagram. Hang on a minute. There's 4 of these. I knew there was 4 of these. There's a shear force loading diagram. See that shear force right there? Can you see that shear force right there? You know where you get that shear force? You get it from a shear force loading diagram. That's where you get it. That's why these diagrams are so important. Because from the diagrams, you get the normal force, the torque, the bending moment, and the shear force to plug in those stress equations to give you the stress. And remember, it's stress that we're after. Well, there's one more kind of loading, and that's these pressure vessels. See, today's topic is pressure vessels. Yeah, and here's the thing. All this time, we've been pretending like you only have one kind of loading happening. But you can have several going on at the same time. We'll talk about the pressure vessels here in just 1 minute. And that'll be a 5th kind of loading. But here, let me give you an example. See, I've got my ruler here, and I can bend it. Already? Da-da, da-da. Can you see I'm bending that ruler? Well, you know what? I could also twist it. I don't know if you can see this, but I don't know. Can you tell? I don't want to break this nice ruler of mine, but can you tell I'm kind of twisting it. I'm twisting it. But did you know what? I could do both at the same time. Now watch this. I'm going to bend it, and I'm also going to twist it. Can you tell? See, there's my ruler. I'm going to bend it. I think I just heard it crack. And then I'm going to twist it. See, I'm twisting it. You know, I could pull on it at the same time. See if I pull on it, I put tension on it. Do you understand that you could have all of these going on at the same time? They call that combined loading, or I call it general loading. And to find the stresses involved, well, you got to figure all of these. But there's one more kind that we got to talk about, and that's the pressure vessels. And that's when you have a container and it's under pressure. You have to, make sure it doesn't leak. Then you pump it up and it's got a lot of pressure inside. And there's two kinds here. There's cylindrical and there's spherical on page 414. So let me erase all this wonderful stuff so you know what we're talking about now. But we're going to add one more kind of loading, and that's this pressure loading business. So let me erase all this. Unless there's a question. Any comments or questions from anybody? You're working on your exam, but I don't think this stuff is on your exam. I don't remember, but I think your exam is over chapters. Let me look this up here. Your exam is over chapter 6 and 7. Well, we're going to talk about chapter 8. That's what we're going to do now. Chapter 8. I just spilled all my papers all over the place. I hate that. Dropped my book, lost my place. Okay. Here's your homework. You can look that up. You don't need that. Okay, well, let's see if I find my place again. We're talking about pressure vessels. Now, where the heck did they go? Yeah, here we go. Getting close now. Yeah, here we go. Now, there's two kinds. There's a cylindrical kind and spherical kind. Let's do the cylindrical kind first. You've probably seen if you go riding around in the countryside sometime. Now I forget, I never had one of these, but it says I think it says butane on it. Now help me out here. Does it say butane or does it say propane? Which is it? Does anybody know? I think they have both kinds. Now, if I remember right, butane, I think it's got four carbons. And 10 hydrogens on it. It's a hydrocarbon. It's made of carbon and hydrogen. That's butane, whereas propane just has the 3. But anyway, you've got a pressure vessel, and what they did was they're just looking at a section of that. Kind of looking at a section of it, of that butane tank, and you know it's under high pressure because when you open the valve, it's under high pressure, and the butane or the propane comes out and lights your stove or whatever you're using there. And what we're going to come up with is this equation here. See, if you looked at this thing has what they call circumferential stress. See, if you made a section in here, now this is just an imaginary section. My artwork isn't that great. We're trying. See, there's a little thin skin here. It's got a thickness. There we go. See, it's got a thickness. We've made an imaginary section, and it has a thickness T. That's how thick the skin is there. And you've got this high pressure, P for high pressure, going on inside your butane tank there. And the sum of the forces on this section right here should be 0. The sum of the forces, that's supposed to be a little t if you can read my writing, the thickness of the skin of the propane tank. The sum of the forces is 0 on everything we do in here. We don't, nothing moves. It's just sitting nice and still in this class. And they have an equation that they came up with for the stress in this skin. See, like if you took a little section of the skin right here, it's got shear stress. They call it circumferential. It's got normal stress. It's got circumferential normal stress. So let me write that word for you. Oh, brother. How do you spell circumferential? I think that's how you spell it. It's got circumferential stress, normal stress, but now it also has longitudinal. Do they call it that? Yeah, well, I'm going to call it that. It's got longitudinal normal stress going this way. Why don't we put a little C under the circumferential and put a little L under the longitudinal. Now it turns out that the circumferential normal stress is bigger than the longitudinal normal stress. And we're going to show you where the equations come from here in just a minute. But how are we going to do that? Well, one way, let's get the longitudinal first. We're going to get the longitudinal normal stress first. See, the rest of the pressure vessels over here, I just took an imaginary section, and there's pressure from it pushing on the butane in this tank here. And I don't know what the pressure is, but it could be something like maybe, I don't know, 50 PSI. I don't know. I don't really know how high it gets. But it's got pressure there. And if you knew the radius of this, if you knew the inside radius of the pressure vessel, you can get that force going to the left. Here, I'll do it in red. There'll be a force going to the left, and that force will equal pressure times the area. See, the way pressure works is pressure is force divided by area. And so force is equal to pressure times the area. Can you get from here to here? This is a definition. Okay. Well, the area in this case is just pi. Let's see, it's the pressure times pi r squared. Ta-da, we got forces going to the left. Well, there's got to be a force going to the right. Now, where does that force come from? Well, you see this skin here has tension everywhere, normal stress, and that accumulates. And the total force going to the right will be the normal stress times this area. Here, let me color it for you. I wonder if green will show up. Probably not, but we'll try. See, what I'm doing is I'm coloring the skin here green. It kind of came out black, didn't it? It's supposed to be green. Well, the total force going to the right, I'll tell you what it is. It's equal to the stress times the area of that green part, which is, well, the length of it is 2 pi r, and the thickness times the thickness. Does that make sense? That if you take the stress times the area of that green area, which is the circumference times the thickness, that's the area of it. That's the force going to the right. And see, this force here, that's going to the left. Now what we're going to do is we're just going to set those equal. They got to be equal because some of the forces are always equal in this class. So we have sigma 2 pi r t equals pressure pi r squared. And now we're going to solve for sigma. Now keep in mind, now this is the longitudinal normal stress, and it will be, well, there'll be a p there. The pi's cancel, and one of the r's cancel, and you'll have a 2t. Boy, Jove, we're done. Ta-da! We just came up with the equation for longitudinal normal stress. Now look in your book, and it's equation 8.2. It's on page 414. And there it is, PR over 2T. But they didn't call it longitudinal, they called it sigma 2. But don't you like to know that it's the longitudinal? It's going along this way, along the axis. Okay, now let's do the circumferential. All right, we'll do the circumferential stress now. I'm going to section this butane tank. I'm going to section it differently. See, here's your tank. Well, really, the tank is like that. Yeah. Only you wouldn't see that part. See, I'm gonna cut this tank in half. Oh, I'm no good at this artwork jazz. I don't think you'd see that part there either, would you? No, this is what you'd see. It looks a little bit more like a cattle watering trough. Sorry about the bad artwork, but we're trying. You see, there's a top half, but we've sliced it off. Now don't forget. Now Well, if you sliced it off in the middle, you wouldn't have that. I tell you what you'd have is you'd have this here. Little artwork here. And then this goes like, yeah, that's not too terribly bad. You kind of get the idea there. And see what you have here. We'll put some dotted lines in here. What you have is a force downward from the top half of the tank. And that force is equal to the pressure times that area. Well, that area is equal to, well, you know what? This is the radius of the tank. So this here would be 2 times the inner radius. So it would be, that area would be 2 times the inner radius times the length of the tank. We'll call this the length of the tank. So that total force going down is the pressure times 2RL. 2 times the radius times the length. Well, there's got to be a force going up because the sum of the forces has to be, hey, the sum of the forces has to be 0 in this class. This here, that was wrong. This is the force going to the right. The sum of the forces is 0. Okay, what do we got going up? Well, we got some forces going up because there's tension in this skin here. You know what those are? Those are circumferential stress. There's stress, and it's the circumferential stress. We'll put sigma with a little c there. See, you got this force going down, but the total force going up is, this is the total force going up. Well, it would be the circumferential stress times the area that it's applied. Now I'm going to color it green. Here we go. I don't know if it's going to come out green on your computer screen there, but I've got kind of green here on mine. Yeah, there's your area. And yeah. Well, what's that area? Well, it's the length times the thickness, isn't it? Yeah. Oh, wait a minute. Times 2, because there's 2 of them, right, guys? There's 2 of those green areas, and each one is L, the length of the thing, times the thickness. Boy, Jove, we've got it. This is the forces going up, and this is the force going down. And what we're going to do is we're going to set them equal. Okay, here we go. Forces going down are P2RL. Forces going up, circumferential stress, LT2. And now we're going to solve for the circumferential stress. I'm going to call it sigma little c. I think the book calls it sigma with a little 1 in there, but I like the c because it tells me what it is. And here goes. It's going to be P. When you solve for that stress, you'll get a P. The 2's cancel, the L's cancel. And it looks like P over RT. P over RT. Is that what the book got? Look and see. No, I did that wrong. No, the R goes here in the numerator. I did bad algebra there, folks. It's PR over T. There you have it. Hey, that equation's in your book. Look, it's that's equation 8-1, and it's on page 414. We now have the equation for circumferential stress in a pressure vessel, a longitudinal pressure vessel, or a cylindrical. That's the name of this. This is a cylindrical pressure vessel. And I want you to compare these two equations. Here they are. You know what? The circumferential stress is twice as big. So that's got a 2 in the denominator. That's why I drew it twice as big. See, if you take a little stress element, you'll be seeing more of these stress elements. And you draw that little stress element, it's on the skin of your cylindrical pressure tank. You've got your longitudinal stress, and your circumferential stress is twice as big. Isn't that interesting? Twice as big on the circumferential stress. I think maybe that's why, you ever see those balloons that the clowns blow up? They're real long, but they're real narrow. Have you seen those balloons? They're real long. They may be like 2 feet long, but they're only about 1 inch in diameter. How come they don't blow up big and round? Because the circumferential stress, where is it? It's bigger. It's harder to blow up. I don't know if that made any sense. And then finally, there's spherical pressure vessels, and you might see some of those sometime if you drive over by the refinery, the gasoline refinery over there on the west side of the river. There's a picture of one on page 416. Let's do that now. Let's get the cylindrical. Any questions so far? Any questions so far? Gee, that silence kind of bothers me. I wonder, let me see if anybody's still out there. Yeah, we still have a good crowd. Let's put it this way, they logged in. I don't know whether they're still with me, but they logged in all right. That's good. Okay, I'm going to erase all this, and I'm going to do a spherical pressure vessel. Here we go. We'll erase all that. Pretty fascinating stuff. There's a apocryphal story about some fellows that went in one of these spherical pressure vessels. Here it is. Ta-da. Spherical pressure vessels. Here we'll add a little artistic license here to kind of give it that 3D look. Of course, there's a way to get in these. These are supported, you know, by these supports, and they put the gasoline there, and it's under a certain amount of high pressure. And they emptied one of them out, and the fellows got in there, and it was awfully dark, and there was a little bit of gasoline left in there, and they forgot their flashlight. So one guy said, "Well, I got a match." You can guess the rest of the story. It's just a joke. Well, let's do that, and we'll get our equation for the spherical pressure vessels, and then we'll work some problems. Here we go. Now, what we're going to do is we're going to take an imaginary section, and we're going to just cut this thing right down the middle. And what I do is I do this with my imaginary chainsaw, my virtual chainsaw. So it's been a while. I haven't worked a chainsaw in 2 or 3 years. Just let me see if I can remember now. First of all, let me see. Yeah, the chain moves pretty good. It's lubricated pretty good. Let me push this little button here to lubricate it a little bit. I'll push that and kind of move the chain. Yeah, I got some oil in there. And then I'm turning the switch on. Switch on. Okay. Yeah, I got the switch on. Oh, and then I need to pull out the choke. Okay, I'm going to pull out the choke maybe pull all the way. And then I got the switch on. I pull out the choke and boom, nothing happens. Boom, nothing happens. Maybe I got too much choke. Let me push the choke in just a little bit. Boom, 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 boom. And then I'm going to my trigger finger, boom, boom, give it some lubrication with my thumb there. Shove in some of that oil. Boom, 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 boom. Now let's make our imaginary cut. Are you ready? Here we go. I've got my chainsaw. Boom, 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 boom. Got it. We just cut it in half, and now we're going to take a look at it. And here's our section. When I actually have a class and the students laugh at that, that was supposed to be funny, by the way, if you didn't catch that. The ones that laugh, of course, their grade goes up. And let's see, this has a little thin skin here. I'll make this thin skin. There we go. There's your thin. Kind of hard for me to draw, but I'm trying. There's your skin. Now the rest of this, we cut it away. It's gone, and we need to kind of make this dashed, I guess, because I think, yeah. No, I should have made that one dashed. Oh well, you got the idea. And it's the same kind of thing. There's going to be the other half of your pressure vessel. We're doing a spherical pressure vessel. It's under pressure, and it's going to be pushing, and it's going to have a force going to the left. And that force is going to equal the pressure of the, whatever it is, gasoline, let's say, inside the tank times the area. Well, the area of that, if this is the radius, the inside radius r, that area is pi r squared. Ta-da, that's it. Take the pressure times the area. You got the force going to the left. Now, what's going to the right? Well, going to the right, you got stress in this skin here, and it's under tension. And you've got stress. You got normal stress, and the rest of the pressure vessels, of course, pulling you to the right. Now the total force going to the right is going to be that normal stress times that area. Here, I'll color it green. Okay, we're going to color, it's just this skin here. We're going to color this. We tried to color it green. There we go. And that area of that skin, well, that's the circumference, 2 pi r times the thickness t. That's the area. It's the distance times the thickness. Distance is the 2 pi r. Now we're going to set these equal. See, this is the force going to the left, and this is the force going to the right. Set them equal. P pi r squared equals sigma 2 pi r t. Now when you solve that, you'll get the normal stress in your spherical pressure vessel to be P R over T. Boy, Jove, that's it. And wait a minute, what happened to the 2? I forgot it. There it is. It's PR over 2T. You'll see that equation on page 415. You know what? That's the same equation that we had. It's the same equation we had for the longitudinal stress in a cylindrical pressure vessel. Okay. Well, good. Now the theory is over. We're going to work some problems now. Do you have any questions before we work some problems? Well, all right. Let's work some problems. I need to erase all this stuff so we can work some problems. I wanted to work 813. It's on page 419. All right. Well, let me erase all this. We've got our equations now. I think we're okay. So we've come to the end of all these equations. We just need to put them together. Now, what you got here is a cylinder. And let me draw it. You've got a cylinder. It's of it's of diameter 24 inches. 24 inches diameter. You'll see it there in your book on page 419. And we have a steel hoop that we want to put around it. But there's a problem with this steel hoop. Let me draw it for you. We have a steel hoop. And it's got a width of 1 inch. Our artist's rendition. See, it's got a 1 inch width and thickness of a 1/4 inch. Here, it's kind of hard to draw, but I'll try. It's got a thickness of a 1/4 inch. Kind of like that. I think you'd see this. Wouldn't you see this bottom part kind of like that? Artistic. Yeah, there you go. See, you got a ring. Isn't that what they call it, a ring? And a hoop? No, they call it a hoop. They call this thing a hoop. You could call it a ring if you wanted to. And the thickness is a 1/4 inch. You see this little itty bitty distance here? Kind of hard to draw, but I'll try. That is 0.25 inches. Kind of a thin ring. Now here's the problem. The inside diameter of this ring is it's too small. It's 2399. It's 2399 inches. They want to put the ring or the hoop. They want to put that hoop on that cylinder, but hey, it won't fit. They can't get it on there. It's a little bit too small. So here's what they're going to do. They're going to heat it up. If they get it hot enough, it'll fit on there. You know that? Now, we've studied that. It's been a while. I forget which chapter it is, but we studied that. There's an equation that goes like this. And this thing here is a lowercase delta, and it stands for, I wonder if, let me ask somebody. I got to find out if you guys are asleep or what. Let me go to my friend Samuel. Samuel, unmute and say hello, please. Oh,
Good morning.
oh, there he is. Hey, Samuel, what does this lowercase delta represent? Do you remember?
How much the length changed?
Yeah, very good. Excellent. That's exactly what it is. Now, the name of that is deformation. It's deformation. But Samuel knows exactly what it means. It just it's going to stretch. See, when you make it hotter, it's going to stretch. Now, what's the temperature? It says here right now it's 65 Fahrenheit. Let's look up this thing, this alpha thing. Now, it's got a name. It's called the oh brother, temperature coefficient of thermal expansion, maybe? We studied it. We'll look it up. Go in the back of your book, but now we need English, senor. When you're dealing with Fahrenheit, we need English. So did they tell you that this here is yeah, it's 836. So look up 836 steel, and alpha is, let me write it down for you. It's 6.6 per degree Fahrenheit, 10 to the minus 6. Can you find that? It's in this flap of your book. My thumb is wiggling on it where it is. And they call it the coefficient of thermal expansion. That's what they call it. What did I say it was? The temperature coefficient of thermal expansion. Same thing. So we got, look at here. We got that. Now the length. Well, the length is really the circumference. Let's figure the length. Now the length is going to be, now they taught me in school many years ago, circumference is equal to pi d. It's equal to pi d. Or you can go 2 pi r if that makes you happy. But this will work. Pi times the diameter, which is 2399 on our hoop. And we can get the length of the hoop. Look at here. We can get the length of the hoop. Now this delta, though, I don't know what that is. We're going to work on that. I tell you what that is. That's going to be your final length minus the initial length. Now the initial length, here, let me write these down. That is the initial length of your hoop. But see, the final length of your hoop, you want to be pi times 24 inches. See, and if you take the final length of your hoop and you subtract the initial length of your hoop, you'll get your deformation of your hoop. We can get these. The final length of your hoop, you can get that. You got a calculator. The initial length of your hoop, you can get that. You got a calculator. And look, here's an equation. Really, there's only one unknown. You can find that delta T. Now, I'm going to shut up, and I'm going to give you 2 minutes if you need it. I'm going to be quiet. It's time for you guys to do something. Don't let me have all the fun. I'm going to let you find the change in temperature there. Go for it. Okay, I'm gonna start putting what I think is L1 and L2 up here. I'm getting for L1, 75 point blah, 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 blah. And for L2, I'm getting 75 point blah, 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 blah. And see, now I can subtract those and I can get this deformation. Here it goes. I'm going to subtract these now. All right. Minus 75.3668. Okay, I did that. It's not very big, guys. I'm getting a deformation of 0.0314 blah, blah, blah inches. That's how much the hoop stretches. And now I'm going to solve for the temperature change. Here goes. So I have to divide and then do something else. Divide by this. 75.3668. I think that's it, guys. Ta-da. I got an answer. I found the change in temperature. I have a change in temperature. Well, let me ask one of you guys. Let's see if anybody's awake out there. How about my friend Mohammed? Mohammed, did you get that temperature change?
Yes, sir.
What'd you get?
I got 63.15.
That's what I got. I'm just going to round it off. Now, if you started off at 65 and you made a change in temperature of 63, then we're going to get the final temperature of 128. Go to the back of the book. Let's see how we did. We'll see if we make that thing 128 degrees. This is problem 813. It should just slip over the cylinder. 813, it says here. 128, yay, we got what the book got. That's what the book got. Well, they rounded off, but let's don't fight over it. They got 128. Now let's keep going. Now, wait a minute. I want to hear some ahas. Did anybody else get 128? Or else the... Yeah, there's somebody. Or really, the 63 is what you were trying to get. Anybody else? I need another aha.
Yes, sir.
Yeah, we're doing great. Now keep reading. And it says here, all right, so we're going to heat it up to 128. The ring will slip on. And then what happens? Well, what is the pressure the hoop exerts on the cylinder and the tensile stress in the ring when it cools back down to 65? Okay. You understand now that we put the hoop on here. It's on here. It's the artist's rendition here of the hoop. And there it is. Kind of hard for me to draw, but we put it on there. You can't see that back part. But you get the picture. We put that hoop on there. it just fit, but we had to get it hot. We had to get it 128 degrees. It would slip on there. And now we're going to let it cool back down. We're going to let, you know what's going to happen? It's going to contract and it's going to squeeze. It's going to contract and it's going to squeeze that cylinder, isn't it? It's going to put pressure on that cylinder. Now we have an equation for that. We have two equations. I think the one we want is this one here for the circumferential stress. And it goes PR over T. Remember, we just talked about that. You're definitely going to have tension in that hoop. It's under tension and it's squeezing. It's putting pressure. See that P right there? Can you see that P? It's putting pressure on your cylinder. We know the thickness of the hoop. It's 0.25. We know the radius. Well, in this case, it would be 12 inches, wouldn't it, for the radius? We know a lot of stuff. Yeah, let me write the stuff we know. We know the radius of the hoop. Let me make some room here. The radius of the hoop is, well, it's 12 inches. No doubt about that. The thickness, we know the thickness. The thickness is 0.25 inches. We know how thick it is, got that. Now what they want us to find is the pressure that hoop puts on the cylinder. If we could only find this, if we could find the normal stress, the circumferential normal stress, then we could find the pressure that it exerts on the cylinder. Now, how are we going to do that? Well, here's the big plan. I just need a little room here to operate. We had a thermal deformation because we heated up the hoop. And when it cools back down, that's in a sense going to be the normal deformation. It really can't contract, but it's not going to contract, but if it could, I don't know how to explain this. We know what this is. We figured it out. It's alpha L delta T, and we know all of those things. But what is the deformation? Well, we had an equation that we learned long ago. Do you guys remember this equation? Normal deformation is NL over AE. Does that ring any bells? I think that's what we're thinking. We're thinking the one way of putting it is this. We could have expanded this hoop instead of by making it hot by just increasing the tension in the hoop, the normal force. See, the normal force over the area, that much, you know what that is? That's your normal stress. And the E, we could look up the E for A36. We could look that up, and the L. I think we can get all of these. I know we can get the E. If you look up the E, the modulus of elasticity for A36 is 29 MSI. Let me write that down. It's 29 MSI, megapounds per square inch. So we know that. Okay. Kind of getting lost here. Can you tell? I think we know the thermal deformation. It's this, and we know every one of these terms. It's how much does the how much does the stress give you a deformation? And we have an equation for it. We're doing pretty good. But I don't know what the temperature, I don't know what the force is. I don't know what the sigma, the stress is. Hey, you know, those links cancel anyway. We could get rid of the links. They're not important. Let's do that. We could get rid of those links. We don't need them. We know the alpha. We know the change in temperature. We know E. But what is the stress? Good question. Okay, well, let me let me see if I've scribbled anything down here to where I can figure this out. What are we doing? 813? Okay. All right. Thought I had it. I thought I had it. Just a second here. Hey, we already know what this delta is. Let me rewrite this. We already know what this delta is. We did it before. It's L2 minus L1. I had that on the board a minute ago. Let me write them again. L1 was 75.3665. L2 was 75.39822. And when you subtract them, what you get is 0.03124 inches. Okay. Well, so what? Well, we know what the length is. We know what this is. That's your stress. Here, let me write it like this. That's your stress times your length over E. And for the length, we got the length that's right here. It would be L2. We got all of these. Let me write it where you guys can see it. I need some room here, someplace. There's a little bit of room right in here. Okay, we have your stress times your length, which is 75.39822 inches over 29 MSI equals 0.031424 inches. Do the units work? I think they do. I think they work. And hey, we can get our stress, and we'll have our stress, our circumferential stress. Do that for me, and tell me what our circumferential stress is going to be. Here goes. Sorry, I got lost there. All right, here we go. We're going to take 0.031424. 0.031424, okay, times 29 e to the 6 divided by 75.39822. Ta-da! Well, I got a humongous normal stress of 12.086 KSI. And you know your R, it's 12 inches. That R there is 12 inches. And that thickness is 0.25 inches. So plug in that normal or circumferential stress and solve for the pressure. Go for it. I'm going to do it. Okay, I got an answer. And the answer is that the pressure of that hoop acting on that cylinder is 251.8 PSI. Okay, let's see how we did. And then we'll work another problem. Oh, gee, I wanted to work another problem. I got stuck on this one and it took a while. We're not going to have time to work another one. Maybe I could get started on another one. All right, now let's look at the answers. 813. Go back here and we'll see what they said. They said 12.1 KSI. They didn't get this. They got 12.1 KSI. So we did okay. We got 12.08. They rounded off. And they got, the book got 252 PSI, which is what we got. They rounded off. And how did we get all that? Well, we used a formula. I don't know if you remember this one. We used a formula for linear deformation, and it took me a while to realize that we knew what the linear deformation was. It's just the difference in those two lengths. I thought that problem was kind of hard. I don't know about you guys. I thought it was kind of hard. Do you have any comments or questions on that problem? Well, we have time to get started on another problem, and I wish we had time to do it. But I could get you started, and you could finish it. Let me ask somebody. Julian, unmute and say hello, Julian.
Hello.
Hey, Julian, I want your honest opinion. I thought that problem was kind of hard. What did you think?
Yeah, I think it was kind of hard. I agree.
I agree. Yeah, I think it's kind of hard. Yeah. Well, here, we got 5 minutes. I'm going to get you started on another problem. But that was kind of fun. Okay, we did that. We got their answers, and we used an equation that we'd probably forgotten about. See, the critical thing on that problem was if you could have stretched that hoop using normal stress, I don't know how you'd do it. I guess maybe just they have these things like jewelers have where they measure rings, you know, and they have different size rings. Well, if you had something like that and you took a hammer and just took your hoop and pounded that, get your hammer here, and pounded that in there, you could stretch that, and it would cause a normal stress. And what we did was we set the normal stress equal to the normal deformation equal, you probably should put an in there. Maybe that's what the book used to do. That's the normal deformation, that's the thermal deformation. That was our secret. Oh, I was going to show you another problem. We got 3 minutes left. This is problem F82. And the beauty is, you guys could finish this problem. We have a cantilever beam. It's got a fixed connection. It's got a section here. And I'm just going to talk to you about the external forces for a minute. I've got 2 minutes. You've got 400 kilonewtons here. And this is a half a meter. And what we're going to do is we're going to section this, and we're just going to look at this section. And we're going to put all the forces on that section. Well, you got the 400 kilonewtons. And won't you have to have a 400 kilonewtons going up? Well, of course. So what does that mean on this section here? If you section this like this, can you see that you would have to have a 400 kilonewtons? Equal and opposite, Newton's third law, going down. Now that's just shear force, and that's positive shear going down on a left-hand member. This is a shear force, and it's considered positive shear if it's going up on a right-hand member. But you're going to have a problem. This is going to start spinning, so you've got to have a bending moment. And that bending moment, if this is 0.5 meters, can you see that that bending moment is going to be 200 kilonewton meters? You got a bending moment. Well, we got all the red stuff. And what they wanted you to do is they wanted you to take this cross section, it's a rectangle, and they wanted you to find the normal and the shear stress at a point on that cross section. That'd be really good exercise for you to try to do. The answers are in the back because it's a fundamental problem. They took a cross section, but they didn't go in the middle. They went a third of the way up, right about in here. And they wanted you to find the normal stress and the shear stress at that location. We have the formulas. We have the formulas, and I wish we had time to do that, but I got stuck on that other one. But you can do it. You can read it. We're going to have to quit, though, and we will resume next Tuesday at 9:30, right? Yeah. Hey, there's not many Tuesdays left, guys. This is the 19th. Oh, by the way, we meet next Tuesday, but we don't meet next Thursday. That's Thanksgiving Day. So we have a meeting next Tuesday, and then we have a meeting on the 1st. That's it. And then you're going to have your final the next week. We only have 2 more meetings. Okay, I'm going to have to sign off. Here's your last chance to say anything. Speak up now, because I'm going to push this red button. I didn't hear anything. Okay, bye-bye, students. I'll see you Tuesday at 9:30-ish.
My professor.
Bye, have a good day.
Bye-bye, you too.